So, should I start?
Yeah. We were waiting outside. I thought. Or not.
So, yes, good morning, everyone. Let's start. So, this is a lecture about digital logic. In the previous lecture, you learned about the CMOS, right? I mean, MOSFET, the MOSFET device. Okay, so in digital logic, the name says that it's digital, right? So it will be dealing by digital. We mean that it will be dealing with zeros and ones, right? Zeros and ones means have you heard about binary numbers? Okay, so yeah, so digital logic deals with the binary numbers. I mean, in the computer can distinguish between 0 volt and a higher voltage. It can be 5 volt, it can be 1.2 volt. So digital logic means you will be dealing with binary numbers. So and in that case, we will be using the MOSFET as a switch. What is what is a switch, right? Switch is a simple thing. Suppose you have this is the power supply, and you suppose you have a light bulb, right? Suppose this is the bulb. So what is the problem with this circuit? The circuit will be always on and the light will be always glowing, right? So if we introduce a turn on and off function, we need to insert a switch, right? So what does this switch do? So suppose this is a switch. So we represent switch like this, and this can be connected to the circuit. Okay, so I mean, let me. When the switch is on, that means the circuit is connected. Okay, and when the switch is not on, I mean, in this case, the circuit, I mean, the voltage, I mean, the bulb is not getting any voltage, right? The bulb is not connected to any power supply, the light will not glow. Simple. So we represent this on and off by 0 and 1. So when suppose this is connected, when this is connected, we call it as 1. When the switch, I mean this portion, when this is connected, then we call it as 1, and when this is not connected, we call it as 0. Okay, we just represent it. So let's examine this example. Okay, suppose this is a power supply, and I have just shown you this figure. When I mean, when this is not connected, this switch is not connected. I mean, the bulb, I mean, the other circuit is not connected. Then it is called x equal to 0. And when this is connected, then it is x equal to 1. Okay. So let's examine this circuit. Okay. So this is a power supply, and there are 2 switches, not a single switch. There are 2 switches. Okay. So let me draw this in the board. Okay, so let's draw this. So this is a power supply, and there are 2 switches. One is here, and this is a bulb. Suppose this is a bulb, and in a single switch, it's very, very simple, right? I mean, if there is a single switch, then if x equal to 0, the light will not glow, because we told you that x is equal to 0 means the switch is not connected, and x equal to 1 means the switch is connected. So in a single switch case, it's very simple, right? X equal to 0, then the light will glow, and if x is equal to 0, light will not glow, and if x equal to 1, light will glow. This is simple, right? For a single switch case. But for a double switch like this, these switches are connected in series, right? One after another. This is called series. So let me examine that. So suppose this switch is named as x1 and the second switch is named as x2. Okay, now the question is, let's start from the beginning. So if x1 equal to, we have actually created a table. Let's create a table here roughly. Because there are two switches, so there will be combinations. You will see there will be combinations. So let's make a table. This is light. Okay. So let's start with the first combination when x1 is equal to 0 and x2 is equal to 0. What does it mean? That x1 is not connected. I mean like this. This portion is not connected when x1 equal to 0 and x2 is also 0, and that means this portion is also not connected. Now in this combination, will the light glow? No, because the light is not connected to the power supply. Okay, there is a disconnection in the line. X1 is also 0. There is no connection right here, and there is no connection right here. So there is no possibility that light will glow. So if the light does not glow, we represent it as 0. Okay, I'm just putting 0 here because in this case, the light will not glow. If the light does not glow, we represent it as 0. Suppose. Okay, then let's move to the next combination. Okay. So suppose in the next combination x1 is equal to 0, but let's make x2 equal to 1. Okay, so in this case x1 is not connected like previous, and but x2 is equal to 1. But I mean x2 is connected. Okay, like this. Okay, so this portion is connected. So in this case, I mean when x1 equal to 0 and x2 equal to 1, will the light glow? No, because yes, it will not glow because this is connected. Okay, but this portion is not connected. So power supply is not connected to the light. So if x1 is not connected, then the circuit is not closing its path. I mean, the voltage supply is not connected to the light, and the light will not glow. So we will represent this as 0. Okay. So now let's move. We have other combinations as well. Let's increase the table size. So let's go to the next combination. When let's make x1 equal to 1 and x2 equal to 0. In this case, x1 is 1 means x1 is fully connected. So I am representing it like this. So this is fully connected, and this is not connected because we are setting x2 equal to 0. Okay, like this. This is not connected. Okay, let's remove the box. It's creating confusion. Okay, so this is the case. X1 is connected, but x2 is not connected. Will the light glow here? No, this is the same case as the previous because the power supply, I mean this power supply is not connected to the there is a disconnection between the path, in the path. So let's write this here. So if x1 equal to 1 and x2 is equal to 0, the light will not glow. So we will set it as 0. And let's go to the final combination. Where we will set x1 equal to 1 and x2 equal to 1 as well. So x1 is connected and x2 is also connected. Okay, in this case, will the light glow? Yes, because now there is a full connection between the power supply and the bulb. So let's write this combination 1 1, and in this case, as the light will glow, we will represent this as 1. Okay, so this is very interesting because now as you can see that from this table, what you can see that you can see that whenever any x1 or x2 is 0, the light will not glow, right? But when the both switches are 1, then the light will glow. And this thing is called AND operation. Let me write this. This truth. I mean, this table is called a truth table. I'll come to the truth table later. But this table is a logic table. I think you can tell because there is a logic because x. I mean, if we are imposing some conditions, if x1 and x2 is equal to 0, then the light will glow. It will not glow. If x1 equal to 0, then and x2 is equal to 1, then the light will not glow. We are setting different conditions, right? Here. So this is called AND function. This kind of function is called AND function. Okay. So okay, let's. Yeah, I I have said I wanted to write here, but whatever. And I mean, you can see that we are only dealing with zeros and ones. I mean, we are taking inputs as zeros and ones and representing the output as zeros and ones, right? So when we deal with zeros and ones, then there is a algebra, different algebra, which deals with zeros and one, which is called Boolean algebra. Okay, let me show you that. So in Boolean algebra, definitely we will deal with zeros and ones, not other numbers. So there are some obvious operations here, but there are some weird operations as well. So as you can see, at the first look at the first equation. It's 0. The dot represents. This dot represents a multiplication operation. Okay, so not 0 0.0, it's 0. The dot should be in the middle. Sorry. So it's 0 cross 0. 0 multiplied by 0. It's 0. We know that. It's obvious, right? But the second, look at the second operation. 1 plus 1. Usually, what is 1 plus 1? 2, right? But we have to deal with only zeros and ones. We cannot go to 2, 3, 4, and etc. So in the Boolean algebra, just remember that 1 plus 1, you cannot go beyond 1. 1 plus 1 is equal to 1. Okay. So this is the second one is weird, yes. But look at the third one, it's obvious. 1 times 1 is equal to 1. In a normal world, it's also applicable. And the fourth one is also obvious, 0 plus 0 equal to 0. And the next one is also obvious, 0 multiplied by 1 and 1 multiplied by 0 equal to 0. And this one is also obvious, 1 plus 0 and 0 plus 1 equal to 1. These are obvious because these operations does not go beyond 1, right? But let me ask you a question. What will be from these operations? Can you tell me 1 plus 1 plus 1? What will be the result?
Also 1.
Also 1, yeah. 1 plus 1 plus 1 and multiple ones will result in 1, not 2, 3, 4, etc. So yes, and 1 plus 0 and 0 plus 1 equal to 1. This is also obvious. And we will learn a new notation here. If x equal to 0, x is some kind of variable. Okay. If x equal to 0 and the opposite of 0 here, what will be the opposite of 0 in Boolean algebra? What should be? 1, right? So we have to deal with 0 and 1. So the complementary, I think this is called complementary. Okay, the opposite one. If x equal to 0, the opposite one will be 1. So the opposite thing is represented like this, x, and there is a bar over x, right? So something, a bar means opposite. Okay, so if x equal to 0 and 0, you put bar over a 0, it will be the opposite. Let me just make it clear. So if you put bar over 0, this is a kind of operation, and it will just convert this to the opposite. Okay, so what should be the value of 1 bar? 0, right? So yeah, or the opposite of 1 is 0. Okay, so this is some Boolean algebra operation. And let's go back to the that we called AND operation. So what can we call this? We can call this as x1 times x2. I will describe that. We can call this function, I mean the AND function, as x1 times x2. Why? Let's check the truth table. You will understand that. So I am telling it that this is an x1 dot, I mean x1 into x2 operation. How? Let's check the this is the output. Okay, so this is the output. So as you can see that if I put the first two values, I mean x1 0 and x2 0. So I'm writing x1 as 0 and x2 as 0. According to the Boolean operation, what will be the result? 0. 0 times 0 is equal to 0. Okay, and let's go to the second operation. I mean second combination, where x1 is equal to 0 and x2 is equal to 1. So 0 times 1, what will be the result? 0. 0. That's what it is. And also check the output here. Because when we set x1 0 and x2 0, the Boolean operation says it will be 0. And in our case, from the circuit analysis, we also got that got the same output. Okay, so in the second case as well, 0 times 1 is equal to 0, and you can see that just multiply them. So 1 times 0 is equal to 0. Okay, 1 times 1 equal to 1. So now you should believe that this output is simply x1 times x2. Okay, so these are related. Okay, so what we have learned from this, we learned that if these two switches are connected in series, then we can represent the output as multiplication operation. Okay, and simply this is the multiplication operation, and we call it in the logic circuit, we call it as AND operation. Okay, so this is an AND operation, and I think after we've finished all the basic operation, then you can compare what is the difference. So we'll come back to it later. Just remember that this is, if we connect two switches in series, then it will create an AND operation, and this is simply if we represent the switch as variables x1 and x2, this is simply a multiplication operation, and this is also called an AND operation. So let's move to the OR, and then you will be clear about this AND operation. When you will have a whole picture, then it will be more clear to you maybe. So let's move to the next circuit. This is very simple. This is the circuit. Suppose now this switch, the two switches are connected like this in parallel. Suppose this is the bulb, a light. Now this is x1. This is x1 and this is x2. Okay. Now what is the difference between these two circuits? Simply they were in series and they are here in parallel. How do you say this is parallel? When the two terminals, I mean the x1 has two terminals, right? This terminal and this terminal, and x2 also has two terminals, this terminal and this terminal, and both terminals are connected. So then we call this as parallel. Okay, so let's analyze this circuit again. So let's make a table. Okay, let's give it a proper name. This table is called truth table. Okay, if we make a table like this with all the combinations of the logic function, then it is called truth table. So we will call from now we will call this as truth table. So let's make a truth table for this circuit as well. This is x1, the second variable is x2. Okay, so I'm writing again light. Okay. So let's start with the first combination when x1 is 0 and x2 is also 0. Okay. So like this, this is already I have drawn the circuit in this configuration where x1 is equal to 0 and x2 is equal to 0. Let me remind you that x1 is equal to 0 means not connected. I mean x1 is 0 and x2 is equal to 0 means not connected. Okay, like this, I have not connected the switch, right? Yeah. So in this case, will the light glow? No, because yes, this is there is no way that light is getting connected to the power supply, right? You know, from this path as well, from this path as well. So will the light will not glow. So we will represent this as 0. Okay. Now let's move to the next combination where x1 equal to 0 and x2 equal to 1. So here x2, let's connect x2 because in this case x2 is equal to 1. We're just testing all the combinations of x1 and x2 like this, and putting it into the table. So in the next combination, let's assume that x1 is equal to 0 and we have connected x2. X2 is equal to 1. Now in this case, will the light glow?
Yes.
Yes, right? Because there is a path. As you can see that the power supply is connected through this path to the light bulb. Okay, so the light bulb will be connected via this below line to the voltage supply. Okay, so the light will glow. So we'll represent this as 1. Okay. Now let's move to the third possible combination where x1 equal to 1 and x2 is equal to 0. Okay, so so let's move to the third combination where x1 will be 1 and x2 will be 0. And let's change the circuit according to this combination. Okay, so in this case x2 is equal to 1. Okay. X2 is equal to 1 and x2 equal to 1 means this is connected, right? And x2 equal to 0 means this is not connected. Now in this case, will the light glow? Yeah, yeah, it should, right? Because there is a path. The path is changed, but there is a path. Okay, so through this path, by this path, the bulb will be connected to the voltage source. So in this case as well, the light will glow. In the third case. Okay, and let's move to the last case where I think you have got an idea and you already know the result. Right? If x1 is x1 is 1, let me write in the truth table, and x2 is equal to 1 as well. Both switches are connected. Now will the light glow? Yeah, obviously, because now there are two paths to be connected to the voltage source, right? In this case, right? So the bulb will get voltage from the power supply from this via these two paths. Okay, so yeah, in this case as well, the light will. Okay. This is the final truth table. What am I doing in this truth table? I am actually writing all possible combinations of zeros and ones of the two inputs. Two variables x1, x2. Can you think of a combination that goes beyond this combination? No, all possible combinations are listed here. So yeah, the truth table is where you will list all the possible combinations and the outcome or output of all those possible combinations. That is called truth table. And let me tell you that this is called OR. Let me write the function at first. I will tell you that this truth table or this circuit will implement this function x1 plus x2. Now let's prove that. Okay, let's prove that. How? Suppose we will just how to prove that this circuit will implement this function. Just put all the combinations and check the output. That's how you can just examine that the truth table of the circuit is correctly implementing the function or not. Okay, so let's put x1 all the values here. I mean, as the first combination, put x1 equal to 0 and x2 equal to 0. So what's 0 plus 0? What is 0 plus 0? It's 0. Okay, and this is reflected here. Okay, then let's put the second combination 0 and 1. So 0, what is 0 plus 1? 1. So this is written here. This is matching with the circuit output. Okay, then what is let's move to the third combination. What is 1 plus 0? 1. So this is also matching with this circuit output. And what is 1 plus 1? This is the weird combination. 1. So this is also reflecting here. So now you believe that this truth table or the circuit is representing simply x1 plus x2, and the plus operation is called OR operation in the logic, digital logic. Okay, so let's remember that plus means OR. Okay, and let's move back to the AND operation, and this is AND operation. So the multiplication operation is AND operation. I mean, so multiplication operation is called as AND operation. Okay, so yeah, this is actually the summary. So plus means OR, and multiplication means AND. And what's the difference between the circuit? In the AND circuit, they are series connected, and in the OR circuit, they are parallel connected. Okay, so let's also write this in the summary table. Okay. So OR is parallel connected. OR is parallel connected. I mean the circuit combination. In the circuit, multiplication means series connected. Okay, so this is the summary. Okay. So I have a task for you, simple task, very simple task. Let's discuss this. Okay. So this is a new circuit. Now let's draw it. I've just created a new circuit. So if you see like this is a switch. This is a valve. This is x1, this is x2. This is I mean, in the slide, this these switches are represented as box. That it doesn't matter. It's just a representation, whatever. So box here box is represented as a switch. Okay. So yes. So I have to. I think we have told you that the parallel means plus and series means multiplication operation. But here they are both series and parallel connection. So we have to write the function like this. I mean the x1 into x2 something like this for this circuit. So we have to do this part by part. Okay. So let's what is very obvious. Let's find that which switches are connected in series, which are connected in parallel. So what obvious thing you can find from the circuit? X2, x1, x2. Yeah, they are beautifully connected parallelly. Yeah. Okay. So let's do part by part. Let's. I will deal with x3 later. Okay. So here x1, x2. This portion of the circuit can be represented as they are parallel. So we will write this as plus. Okay. Remember, parallel means plus and series means multiplication operation. Great. Now this portion is x1 plus x2, and let's let's assume that this the circle is a single switch. Okay, and this I think, let me draw this circle as well. So this circle and this circle, how are they connected? In series, right? So the I will treat this as a single switch, x1 plus x2, and the x3 is connected in series with this big circle. So this is the big circle, and I will just multiply this with x3. Okay, so because this portion of the circuit, which can be represented as x1 plus x2, is connected in series with the x3. So for this circuit, we can write this as the whole function. Let's write it more clear way. And x1 plus x2 into x3. Okay, so this is the function for this circuit. Okay, and from this circuit, you can just write the truth table as well. I'm not going to the truth table because the truth table was showing you that these operations, the class operations represent the or. Yeah. Let's do this. Let's do a classwork maybe. I am drawing a random circuit, and you have to just write this function. Okay, like this function. Okay, let's do it. We'll practice this here in the class. Okay, I will represent this as x1, this as x2, this one is x3, this one is x4, and the last one is x5. Okay, so your task will be to write this kind of representation, the function of this circuit. Okay, so let's try first maybe, and then I will show you how to do that. I think you can do that, right?
So x1 plus x2 multiplied by x3 plus x4 x5.
Yeah, exactly. It's very simple, right? So we can see two clear portions, right? This portion and this portion. Okay, so I can write this circle as what? X1, because they are parallel connected, we can write this as x1 plus x2. Okay, so let's deal with this circle next. So these are all connected in parallel. So we can write this x3 plus x4 plus x5. And these two circles are connected in series, right? So we can write this as multiplication operation. So this is it. This is the whole function for this circuit. Okay, so now we can actually write the function of a circuit. So you may wonder that, okay, so these are switches, and how to implement these switches in circuits? Let's discuss that. So we have switch to turn the light on and off, right? Yes, but actually we will make computers, the processors using these switches, because this is a function. If we can implement any function, the computer simply just calculate this kind of operations. Inside the computer, they actually calculate, they do multiplications, they do additions, right? So what is computer? Computer, what does the computer do? It's compute, right? So to compute, we have to do addition, we have to do multiplication, and etc. And so to do the addition and multiplication, these kind of switches are used. So suppose if we need to add something, then we use or function. If we want to multiply, then we need to use the and function. Okay, so inside the computer, this kind of operations takes place. But do you see switches like we use in lights inside the computer? In the computer, not a single, only, here this is only one addition operation, but in real life, the computers do millions of these operations, multiplication, addition, in a second. Okay, million times or million times, whatever. So yeah, so and you will have not this. There are 5 switches there, right? But to do, I mean, if you want to add 1,000 numbers, okay, then you need 1,000 switches. This is small, but in real life you have to do. You will have billion switches, okay, to do complex operations. So, do you think the switches we use to turn on light on and off, it can be embedded inside a computer? Billion switches, it's not possible. So we cannot use typical on-off switches for that. So we need to use very small switches. I mean, in nanometer scale. Do you know what is a nanometer? How much is small? I think in the first class, Dr. Aziz gave you an idea of how a nanometer is. Okay, so a nanometer, you cannot just realize how. I mean, our brain cannot realize how a small nanometer is. So it's like, let's try this. For 10 to the power 9 meter. 10 to the power 9 meter means one. Suppose you have 1 meter, and you have a 1 meter scale, and you divide this. Let me write. Yes. So if you divide 1 meter by this number, then you will get 1 nanometer. I mean, this is too small. Our brain cannot realize it. So whatever. So in nanometer scale, you cannot just use the switches we use typically to turn on and off lights and fans, lights and ACs, etc. So we need very small switch. So how can we find small switch? It is related to the previous class. Yeah, you have heard and you have learned about MOSFET, right? In the previous class. This is a simple transistor. So in transistor, the transistors acts as a switch. So I mean, this was a MOSFET symbol, and if you follow the previous class, you will learn that it's MOSFET. It's a transistor. Transistor can be made very small, like in nanometer scale. Okay, so transistor and MOSFET. This is a MOSFET. MOSFET is a simply 3-terminal device. Why I'm telling it 3-terminal? Because we learned about resistors, right? A resistor was a 2-terminal device because it had 2 terminals, simple. But this device, the MOSFET, I think you have heard, you have learned the structure of the MOSFET. I'm not going through that. Just treat this as a switch. How this works as a switch? Okay, it's a 3-terminal device. Like transistor is a 2-terminal device, but it's a 3-terminal device. So I can you can compare this MOSFET switch as a water tap maybe. Okay, so suppose you have a water tap. What do you do? This is I'm not good at drawing. So suppose this is a tap, water tap. Okay. So suppose this is a terminal where water comes in, right? Water in, and this is one. I'm treating this as a terminal. In one terminal, the water will be in, and in other terminal, the water will be out. Okay. And there is a switch here. You can control this switch to control the water, right? When you I'm turning on this switch, I'm representing at this as 1. So suppose if the switch is 1, then the water will flow, and if this is 0, then the water will not flow. I mean, you will turn off the switch. So this switch, this is a controlling point. So this is one, and this is other terminal. So this is a control terminal maybe. So the tap is a 3-terminal device, right? Water tap is a 3-terminal device where the water will be in one terminal, water will be in, and in the other terminal water will be out, and there is a control terminal. In a similar fashion, MOSFET also works in the same fashion, right? Because there will be two terminals, like they are called as this is source. This is termed as source. We just represent it as S, and this is drain, and this is gate. Okay, so you can the main controller is the gate. You can just use this gate to control the current from drain to source. Okay, so let me draw this line this way. Suppose there is the same power supply we are talking about, the power supply, and this is the line. Okay, so we have to use a switch here. Suppose we will use a MOSFET. What will the MOSFET do? If we input one, I want to turn the switch on. Okay, so then I need to put one in the gate of this terminal. The gate, and this is, suppose this is drain and this is source. So what will this do? If we insert one, then what the MOSFET will do? It will just connect the drain and source. Okay, it just simple. I'll think simply, very simply. When we insert one into the gate, the MOSFET will connect drain to source. What we told you as connected. Okay, so simply in the previous circuit, as you can see that when let me just bring that out. Like here. So if we put x1 equal to 1, then the switch was connected, and if we put x1 equal to 0, then the switch is not connected. As simple as that. Okay, so the MOSFET implements the same thing. Here we have told you theoretically. Theoretically means if we put 1, the switch will be on. If we put 0, the switch will be not connected. So how will this be implemented in the circuit? Okay, so this will be implemented through a MOSFET. MOSFET does the same thing that I have described in the switching operation. When you will put 1 in the gate, the drain and source will be connected. This will be connected. And if we put, suppose gate equal to 0, if we connect as gate equal to 0, then the drain, the two terminals of the MOSFET will not be connected. Okay, so then what will it do? If gate equal to 0, the drain and source not connected, there this will be like this. Like this. The drain and source are not connected. Okay, so I'm just this is gate. So if I put gate equal to 0, the drain and source will be like that. No connection between drain and this will act as 0. Okay, and if we put gate equal to 1, then the drain and source will be connected. Simply. So what we have told theoretically in the previous circuit, x1 equal to 0, whatever I told that if we put x1 equal to 0, then this will be disconnected, and if we put x equal to 0, the x equal to 1, then it will be connected. So this is how it is implemented. Okay, so the MOSFET can do this switching operation, and MOSFET can be built in nanometer scale. Very small. You have learn about the structure of the MOSFET. I'm not going into the structure of the MOSFET. I'm just using the application of a MOSFET, which is we can use the MOSFET as a switch. And in real life, the computers are made of these MOSFETs. Okay, the MOSFETs are used as the computer. The mobile and the computer use. There will be in the chip. There will be millions or billions of these MOSFETs inside the chip or in the processor, in the memory, whatever. This is those circuits, and the chips are built using this building block. MOSFET is the building block of your processor or of your memory. Okay, so your processor and memory is nothing but a combination of billions of switches, and the MOSFETs acts as a switch. Okay, okay, so So, we have learned about AND operation, right? And or and in the circuit, they are represented as a block like this. We have represented resistor as what, like this in the circuit symbol, right? We represent a resistor like this. So to represent AND operation, we use this kind of blocks to represent AND. We have already talked about AND. So this is the symbol of AND gate, and this thing is called gate. Okay, so this is AND gate, and this is the truth table of AND gate. We have already shown you the truth table of AND gate. I mean, the series connection is simply the AND gate, and if you match the truth table, we represented the inputs. The switches are treated as inputs here. So this A and B here are x1 and x2. Okay, so inputs, I mean the switches are represented as a different way. So some people represent it as x1, x2, x3, x4, dot, dot, dot. And some people represent it as A, B, C, D, or whatever. So this is actually a two input AND gate, and this is OR. We have learned about AND and we have learned about OR. Okay. Now you can see there is another operation, I mean after AND, which is NAND. Okay, so what is a NAND operation? Let's go back. This is messy, so let's go back to the slide. So this was actually AND operation when the switches are connected in series. Okay, so if we just invert the output, make the truth table of AND first. Suppose this is x1, this is x2, and the AND output is x1 dot, I mean multiply x2. So 0 times 0 is equal to 0, 0 times 1 is equal to 0, 1 times 0 is equal to 0, and 1 times 1 is equal to 1. Simply this is an AND operation. So this is AND, and I am extending the table. Did you remember in the first section of this lecture, I have shown you a representation of bar. Bar means the inverter, right? If 0 bar means 1, 1 bar means 0. So if you invert the Boolean value, then it is called a bar, or and this is the operation you can this is an operation actually. So this operation is called as NOT. Okay, and there is a gate which is called NOT gate. I think you have NOT gate, or it is also called as inverter. I think in the previous class you have learned the structure of an inverter maybe. What inverter means is simply invert or make. What is invert or what is inversion? Is to make opposite, right? What I have told you, that opposite means inversion here. So if what is the task of this gate? If you input 0 here, it will just invert it. Invert it to what? To complement, I mean the opposite value 1. So this is if you this gate is, I mean a gate will be called as a NOT gate or an inverter. When we input 0, it will give you 1, and if we input 1, what will be the output of the NOT gate? 0. Just it will, the task of this gate will be to just whatever it gets, it will just invert. So if we invert this result, okay, so how this inverting, let me write this later. So if we let's invert these results, Okay, so if we invert 0, it will be 1. If we invert 0, it will be 1. I'm just inverting every elements of this outputs. It will be 1 and this will be 0. Okay, so then actually this makes another truth table, and this and because this is inverted, we can write this as x1 x2 bar, right? If this is I'm just inverting x1 x2 result, right? So let me, there is a bar here. Okay, so these 4 results are for x1 into x2, and this one are for the inverted result. So we represent this as x1 x2 bar. We put a bar over x1 and x2 because this is the inversion of x1 into x2. And this, if this is AND, this operation is called NAND. Okay, I am putting an N in front of AND to represent the inversion operation. Okay, so this is a NAND result actually. And in a similar way, we can do this for OR as well. Suppose this is x1 and this is x2, and this is OR. We represent OR operation using a plus sign. Okay, and way. So let's write the combinations 0 0 0 1 1 0 and 1 1. So 0 plus 0, this is OR operation, right? This is OR. So whenever there is a plus, this is the OR operation. So 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, and 1 plus 1 is equal to what? 1. Yeah, this is the weird combination. And the same thing, we will invert all these entries, I mean all these results. Then what will happen? 0 will be converted to 1, 1 will be converted to 0. I mean the whole opposite. 1 will be converted to 0, and the 1 will be converted to 0. So what will we write here? Anyone? I mean, if yeah, yes, exactly. So this is x1 plus x2, and the inverted operation is called NOR. I mean, I am inserting an in front of OR. This is NOR operation, and we can write the function as simply x1 plus x2. Then we have to put a bar over the function. This is a bar. So the under the bar, this is OR operation, and if we put a bar, and then this becomes NOR. Okay, so trust me, this is the last actually. I mean, we have gone through, and we know AND operation, right? We know OR operation, and we have just learned NAND operation. NAND is simply the opposite of AND, and we have learned NOR operation. Okay, so these are the basic gates, and with these gates, I mean, with these gates you can do any operation actually. So and we also, in the previous class, we also learned about NOT gate. It's a simple gate. Simply it will whatever it will take as input, it will invert the input actually. So we actually covered these functions, and these are actually summarized in this page actually. So this is not and as you can see, this is the representation of the gates. This is inverter is represented as a triangle and a circle in front of it, and don't forget this circle. Okay, so this is NOT gate or inverter, whatever it is, and this is AND gate.
It's a NOT gate, if you don't mind. It's a NOT gate.
Okay, so NOT gate is simply just an inverter. So the function of the NOT gate is simple. It takes a single input. I mean, if x equal to 0, I mean, let's simplify this. If it takes 0 as input, it will invert it to 1. And if it takes 1 as input, it will invert it to 0. Simply just invert. Yes. Simply this just inverts. Okay, that's why it's inverter. I mean, this is not yet. And let's I mean, let's make it uniform. So I mean, let's write a truth table for NOT gate as well. We have in the truth table of AND, OR, NAND, NOR. Let's see the truth table for NOT gate as well. So here, as you can see that, let me just draw the AND because it will be easier to relate. So this is NAND operation. Okay, suppose this one is x1 and this one is x2. So the AND gate operation, what will do the AND? What will be done at the AND gate? It will just take two inputs and it will just multiply, right? And for OR is represented like this. There's a very small difference between AND and OR gate symbol. This is a straight line and this is just curve. Okay, so what is the function of OR gate? Sorry. If this is it takes two and just add them, because we have told you in the very first section of this lecture that OR gate does addition operation and AND gate does multiplication operation, right? So this is let's go to the AND gate. This is x1 x2. Actually, this AND gate is not limited to two inputs. I have just shown you two inputs, but it can handle multiple inputs. Suppose there is another input which is x3. It can take, but the circuit will be different. Okay, the circuit will be different, let me show you that this one was for x1 and x2, two switches, right? But if we what if we add another switch like x3? Okay, what if we add? Don't mess it here. Yeah, draw a new circuit. Okay. So this is very simple. X1 we had at first we had x1 and x2. Okay, so if we want to increase like x3 and x4, all are connected in series. Suppose they all are connected in series and multiple of them. Suppose x4. Then we have a bulb. The function we can say this as the function will be like x1 times x2 times x3 times x4. We can extend the idea like this. Okay, so we can increase this to 100,000, whatever. So this is not limited. The multiplication operation is not limited to the only two numbers. You can just increase it using the same idea. So this if we use just only x1 and x2, this is called two input AND gate because there are two inputs. Okay, but we can, as I have said, that we can increase the number of input. Suppose we add another input, the circuit will be definitely different. x1, x2, and x3. What will be the output? x1 into x2 into x3. Simple as that. Yeah. So you can add x4, x5, and this will, if we add x4, add the term x4. That's it. Okay, this is simple. Okay, so what does an AND gate do? It simply multiply. Good. Okay, and for for the OR gate, what it does, it simply adds. So if instead of x1, x2, the OR gate takes two input, x1 and x2, it just get the addition operation. If we increase the input, if we add x3, I'm not drawing in a proper way. If we want to make this x3, then we need to make this get symbol larger, and then x3. So what it does, it will take three inputs, x1, x2, and x3, and then add them. So you can increase the number of. So if we have 4 inputs, you will add x1, x2, x3, and x4, and the output will be x1, x2 plus x3 plus x4. Simple as that. Okay, so those will be multiple input gates actually. Okay, so but for the NOT gate can take only one input. Okay. AND gate, OR gate, and other NAND gate, NOR gate, they can take multiple inputs, but NOT gate is a unique one. It can only take one input. A NOT gate cannot take multiple inputs, even it cannot take 2 inputs. It will take only one input and just invert that, because it will take 0, and if you give 0 to its input, it will give you 1. So I am writing the truth table like this. So instead of x1, x2, x3, I am just writing this as x. I mean the input variable as x. Okay. So I'm telling it is variable because the input can be 0 or 1. Okay. So that's why I'm representing this as x, or a variable. Okay, x is the input. It can be 0, it can be 1. So what will be the truth table? I'm writing this at output. So if x equal to 0, the NOT gate output will be 1. If x equal to 1, the NOT gate output will be 0. This is the truth table of NOT gate. That's it. Because there is only one variable, I mean there is only one input. Okay, and one input, and the combination can be 0 and 1. Okay, there is no combination behind this. Okay, so this is NOT gate. A NOT gate is very simple, and it's just take an input and just invert it. That's the operation of a NOT gate. Okay, now suppose using we have learned the gate symbols here. As you can see that this is OR gate symbol, and okay. So how is the NAND gate symbol? Okay, so NAND gate symbol is simple. A symbol is very simple because this is AND gate. If you put a circle at the output like this is, as you can see, this is almost an AND gate, but there is a small circle at the output, and this is represented as NAND. Okay, so this circle, small circle, represents a inverting operation, and I have told you that this simply, if you invert the output of an AND gate, you will get a NAND gate. Okay, as you can see, look at the truth table of AND gate and NAND gate. This is, look at the Y column. Y is the output here. Output is represented as Y here. So as you can see, this 0 0 0 1. But in the NAND gate, the output is 1 1 1 0. Exactly the opposite. Okay, 3 0 1. I mean 0 0 0 1. This is 1 1 1 0. If you, if you invert every row of an AND gate, you will get the NAND gate. Okay. So and let's. This is OR gate. I have already shown you, drawn the symbol of OR gate, and look at the difference between the symbols of OR gate and NOR gate. You have to put a small circle in front of the OR gate, and you will get the symbol of NOR gate. And similarly, see the output of the OR gate and NOR gate. There is 0 1 1 1, and here 1 0 0. Just opposite of OR. Okay, these are just this is called complementary. Okay, if something is opposite, this is called complementary, or there are so many names, right? Not, inverter, complementary. These are all same things. Not operation, inverting operation, complementary operation. These are all same thing. Okay, it just invert. So these are basic building blocks. Gates, and let me just do a small exercise. Suppose you have to do x3 and x4. suppose you need to do this operation. Okay, so you have, and you are told to design a logic circuit to implement this function. I mean, how will you, suppose you have to do this operation inside a computer. Okay, so how will you make this operation? Using logic circuit. I mean, logic circuit means you will be using gates. Okay, the AND gate, OR gate, NAND gate, NOR gate. So let's implement this using gates. So let's go block by block. Let's focus on this operation. What is this? This is addition operation, right? X1, X2, X3. You have to add X1, X2, and X3. So to add, what gate we will need? To for addition operation, AND gate, OR gate, NOT gate, which gate? OR gate, right? Yes. So I have told you the summary of the whole class actually, the first section of the class where I have write this actually. So plus means OR. Addition operation is OR, and multiplication operation is AND. I have written this at the very first moment of this, I mean, first section of this class. So this is the summary. This will be the whole summary of our today's class actually. So let's go back to the function here. So this is an addition operation. So we will need OR gate. Okay. So let's take an OR gate. This is the symbol of an OR gate. I have drawn it big. Why? Because we have to take 3 inputs. So we have to add 3 values. I mean X1, X2, and X3. Okay. So I'm drawing like this. So in this case, what will be the output? I mean, what is the output of this OR gate? Yeah, this gate will simply add what it gets in the input. Okay, it is getting X1, X2, and X3, so it will add them up, right? X1 plus X2 plus X3. Very simple. Okay, X1 plus X2 plus X3. So you have done this operation using this gate. Okay. Also, there is no symbol like this inside the AND gate. Okay, so you have got X1, X2, X3. Right in this OR, these are ORs. Suppose these are ORs. You are giving inputs using ORs to the gate, and this OR you have X1 plus X2 plus X3. Then what we have to do? We have to multiply this portion with this portion, right? So this is a circle. This is a circle, like this, and they are multiplied. They have to be multiplied. Suppose this is our requirement. We have to implement this whole function. So we have already got this X1 plus X2 plus X3, and we have to multiply this X1 plus X2 plus X3 with X4. Okay, so to multiply, what gate we need? AND gate, right? So this is the symbol of AND gate. Okay, and we have to insert this whole X1 plus X2 plus X3 as one input, and what will be the other input? X4, right? Then what will this AND gate do? It will multiply the inputs. So what are the inputs of this AND gate? The first input is the whole X1 plus X2 plus X3 is the first input, and the second input is the X4. So it will multiply this whole X1 plus X2 plus X3 and X4. So this is the final output. So this will implement this logic function. So this is the whole circuit to implement this logic function. Okay, so I think you got it. Let's should we do another example, or you already got it?
I think we're good.
Let's do another example, or should we move? Let's do another example maybe. If we do not compare 2 things, then it is not clear. I think it's because maybe it's a special case. So let's do another small example. Maybe not that. Let's do a small example. Suppose x1 plus x2 and x3. Let's make it bigger. X4. Okay. So we'll do this part by part. You tell me that from where should I start?
X1 plus X2.
Exactly, x1 plus x2. Right. So let's start x1 plus x2. So to do addition operation, what gate we need?
Okay.
OR gate. Great. This is OR gate, and we'll input x1 and x2 because we need to add x1 and x2. And that's why we will giving the input or inserting the input x1 and x2. And what will we get? x1 plus x2. Yeah. And the output of the OR gate. Now we have done x1 plus x2. Now we will move to where? To x3. Okay. So this is a block. This is one circle, and this is another circle. Okay. So we have to multiply these two. So to multiply two things, we will need AND gate. Right? Exactly. So this is AND gate. We have to multiply two inputs, and the first input is x1 plus x2, and the second input is x3 of this gate. Right? This is x3. So what will this AND gate do? It will just multiply the two inputs. I mean, the first input is x1 plus x2. This whole x1 plus x2 is the first input, and the second input is x3. Okay. And we got we got this one. Okay, we have got this one already in this side. Now this whole thing in this second bracket is have to be added. I mean, this whole thing has to be added to with x4, right? So this is one big circle. This is one big circle. We have already got this. We have this already here. Okay, and we just need to add x4 with this whole thing. So to add this, we need OR gate, right? So we'll take another OR gate, and OR gate will take this whole input. I mean, whole function as an input. I mean, x1 plus x2 dot x3, this whole thing, and we will get x4. And we have to add x4. We have to insert x4 as an input, and this OR gate will just add these two inputs. This is the first input, and this is the second input. The OR gate will just make an addition operation between these two. So the final output would be this whole thing: x1 plus x2 dot x3, and then it will just add this with x4. So that's it. This whole circuit. I think this is circuit. We needed 3 gates here, right? 2 OR gates. These are 2 OR gates, and this is AND gate. Okay. So to implement this function, we need 3 gates. Okay. So yeah, it's good. So I think if we give this kind of function, you are now able to just draw the logic circuit, right? So yeah. So actually, I mean, the processor are made like this, exactly like this. Okay, you are now closer to the real life. I mean, with the real life computers works like this. If you these are just simply these are operations. These are simple operations, but in case of computers, this function will be very large, like this. But the idea is the same. Okay, so I mean, in the real life computers, you will have this function will be very much big, and you have to implement with the logic gates. And these logic gates are inside your microprocessor or memory, whatever. So this is how it works. This is how computer works. Okay, I mean, it's implementing some logic functions. By some I mean billions of these logic functions. They actually compute this kind of logic functions using these gates practically in real life. So maybe let's take a break. Yeah. So it's now 11:26. Yeah. After a break, we'll meet again. Thank you.
When should we be back?
Sorry.
When should we be back?
Uh, I didn't ask.
What time should we be back?
Oh, what? Could you suggest?
To you. 10 minutes.
Oh, 15 minutes. Yep. So it's 11:36, right? Oh, sorry, 26. So we'll be back by 11:40. Just like making sense to listen to us.
Yeah.
So. Really, we have told you that we can make any logic function. I mean, the expression x plus plus x plus x, those kind of expressions are called function here. We will call them as function. Okay, so we can implement any logic any function using these gates actually. Now, right now, yeah. So you believe that, right? That we can make any function with these gates, any function, right? So now the question is, how these are just blocks, right? And this is and, but how these and gates are made? What's inside the and gate? I have shown you with switches, right? But yes, but what is the proper implementation? We will go through that. This AND gate, OR gate, an AND gate, whatever it is made with MOSFET. I have told you, and we will show you a proper implementation. I mean, a proper implementation of these gates using MOSFET. And you already have an idea of NOT gate in the previous class, but yeah, let's start from here maybe. So let's analyze this circuit, okay? And before that, let me clarify one other thing. I have told this to you already. This is let me just go to full extent. So here I have told you that this is a gate, right? This terminal is called gate, and this terminal is called drain, and this terminal is called source. Okay. So I have told you that if gate is, I mean, if the gate gets full voltage, I mean one. Let me clarify one thing. So in Boolean algebra, we have 0 and 1. So in circuit, here we represent 0 as in terms of voltage. If we want to represent 0 and 1 in terms of voltage, but I mean circuit voltage. So logical 0 means 0 volt. Suppose in a part of a circuit, suppose there is a 0 volt, we can represent this as 0, and for log 1, the voltage is not exactly 1. Okay. Maybe the voltage can be 5 volts. So that, I mean, in a circuit, suppose there are 2 voltage levels. One is 5 volt and the other one is 0. So the higher voltage level will be represented as logical 1, and the lower voltage will be represented as 0. Okay. So I mean, the logical 1 can be corresponded to 5 volt. Actually, different circuit technologies use different voltage. In the previous MOSFET structures, I mean, in the previous technologies, 5 volt was used as a high voltage. But day by day, this high voltage is shrinking, because high voltage means high power, right? So, but in the modern days, this high voltage level is being reduced. Okay, why? Instead of 5 volt, now 1.2, even 0.7 volt is being used. Whatever, let's just remove this. So let's deal with 1.2. So in modern day processors, we use 1.2 volt as high voltage and 0 volt as low voltage. I mean, we represent 1.2 volt as 1 and 0 volt as 0. This 1 and 0 is just a representation, nothing else. Okay, so the higher level of voltage is represented as 1 and the lower level of voltage is represented as 0. Okay, so you may ask why this reduction? I mean, why 5 will drop from 5 volt to 1.2 volt? Because you know that I have told you that in the microprocessor or memory, there are billions of transistors. And if billions of transistors tries to take 5 volt, actually the power, I mean, the required power will be very much higher. But we do not want that, right? We want to use less power for microprocessor or memory because we want to save energy. So that's why actually the higher voltage level is reducing. Whatever, this is not our headache right now. So the main thing we have to understand here is the higher voltage level is treated as 1 and the lower voltage level is treated as 0. That's it actually. Okay, so sometimes this higher voltage level is represented as VDD. I mean, to represent this as a variable like thing, I mean, to name it something, it's sometimes you will see this as VDD. In the textbook, it actually represented as VDD. That's why I am just clarifying you, so that you can, if you read some textbook or some paper in future, just remember that VDD means the high voltage. Okay, I mean the full voltage. So that's what it's written here actually. Here, as you can see, if the VG means the gate terminal, voltage is VDD. As I have said, the VDD means high voltage, means 1. Okay, so VG is equal to 1. Whenever you see VG equal to VDD, you have to interpret VDD as 1. Simple as that. And 0 as 0. So 0, there is no problem with 0. 0 volt is represented as logic 0. But when you see VDD, which some voltage is equal to VDD, that means it is 1. But I mean logical 1. We represent this as 1. Okay. So if what is written here, if VG is equal to VDD, then what happens? This switch is connected. Whatever I told you that if we insert 1, I mean logical 1 in gate terminal, the switch is on. I mean this is connected. That is what represented here. If VG equal to VDD, I mean VG equal to 1, logical 1, then this is connected. Okay. Why I'm saying it logical 1? Why I'm repeating this? Because logical 1 is a representation, just a representation, but it's not exact 1 volt. Okay. Logical 1 can mean VDD. I mean, what it is 1.2. That's why it's actually written VDD, because in different technologies, technologies means I mean in 2010s they maybe they use 5 volt as VDD. But now they can use 1.2 volt as VDD. Now they can use 0.7 volt as VDD. That's why it's written as a variable like thing, a VDD, not 1.2, 1.5. Because this will be true for all voltage levels. I mean all technologies. Okay, whatever. If the circuit deals with 1.2 and 0, this is VDD will be 1.2. If VDD is 5 volt, then if the circuit is dealing with 5 volt and 0, this is you can write VDD equal to 5 volt. But I'm telling you logical 1. Why? Because logical 1 does not mean that the voltage is 1 volt, right? This is logical 1. When I tell you logical 1, that means the highest voltage. I mean the VDD, right? So that's why I am clarifying that this is, if VG equal to VDD, I mean if we insert 1 logical 1 as input in the gate, then this is connected. I mean this is a switch. I have told you that if X, I mean the input of this MOSFET is input by input. The input is actually gate. Okay, So if the gate is 1, then the switch is connected. If the gate is 0, this is VG equal to 0 volt, and this is let's observe here. The VG is equal to 0 volt. VG equal to 0 volt means it's logical 0. Okay, so if you input 0 in the gate, the switch will not be connected. This will be disconnected. Simple. So, and this is called NMOS. The device here, this is MOSFET, yes, but the short name of this device is NMOS. Let me write it down. So it's called vertically. So this is called NMOS. So in NMOS, I'm writing a summary table here as well for this circuit. NMOS. When NMOS, this is an NMOS. If gate equal to 1, that what I have told you as a switch, that if gate equal to 1 means connected. But I mean, let's write it in short form, on. So on means connected. Okay. So if gate equal to 0, if we insert gate equal to 0, then the device will be off, right? I mean disconnected. By on I mean connected, and by off I mean disconnected simply. Okay, then there is another device. I mean there is a complementary device of this NMOS, which is called PMOS. And this is represented as a what is the difference between NMOS and PMOS? This is PMOS. Let me write that first. This is called PMOS. What is the difference? There is a circle here, and the circuit operation total is totally opposite than NMOS. Okay, I mean the circuit operation of PMOS is totally opposite to NMOS. By this I mean that if gate equal to 1, the device will be off. Okay, you have to just remember this. NMOS is I mean it's a normal operation. You can treat NMOS is a NMOS, but PMOS is a weird device, which means it will act totally in opposite way than NMOS. I mean when gate is equal to 1, this is off. Gate equal to 0 here. If we insert 0 here, the device will be on. I mean, you do not need to remember this PMOS. You just remember NMOS and then just invert the operation. I mean, just remember that the PMOS will be acting totally opposite. Okay, so let's remember this. Okay, so in the case of, I mean, you do not, as I have said, you do not need to memorize PMOS. Just remember that this is opposite to NMOS. So for NMOS gate, if you get if the gate is 1, I mean logical 1, then the device is on and connected, and gate is equal to 0, the device is off. So keeping this in mind, this is what written in the slide for PMOS. Okay, so let's okay. So yeah, so let's analyze this circuit. This will be very easy if we can keep in mind that the operation, I mean the device operation of NMOS, when it is on or when it is off. If we know that, it's very much easy. So let's draw it. So what I'm doing. I have drawn an NMOS. This is ground. I mean this is 0 volt. We represent 0 volt like this. Okay, so this is gate, and this one is NMOS, and this let me write that. This is PMOS, and this is NMOS, and we connect them together, and let's make an input here. So the input is V, and we have a VDD here. So to simplify the case, let's write VDD as 5 volt. So this 5 volt means logical 1. Remember that? So we'll do it later maybe. Okay. So if we take this is our input for this circuit, and this is our output. Okay. Suppose we have designed a circuit. Then let's try. At first, let's try with Vx equal to 0. Suppose we are giving 0 voltage here. Then what happens? What happens to the circuit? It's very easy if you just understand the operation of NMOS. It's very easy. So the gate of this NMOS is getting 0, right? Okay. So for NMOS, let me yeah, that's right here. Okay. So look at this NMOS operation. If gate, I mean the gate of the MOSFET gets 0, then what will the NMOS will be turned on or off? On. Sorry, off. Sorry, you're correct. So gate, as we have remembered that if gate gets 0, then the NMOS will be off. So let's represent like maybe take off here because I have to draw it again and again. Whatever. So 0 means off. So off means there is no connection right here. Okay, I've just erased it. So 0 means no connection. So there will be a vacuum, I mean empty space here. So this thing will not be connected to this thing. Okay, and let's talk about the PMOS here. This same input is also going to the PMOS as well. So PMOS gate is also getting 0. Okay, the circuit is connected like this because the same input will go to the NMOS and PMOS in both NMOS and PMOS. So PMOS is getting 0 as input. So if PMOS gets 0 as input, what will be will it be on or off? On. Yes, because as I have told you that this is totally opposite to NMOS. If NMOS gets 0, it turns on, but in case of PMOS, it gets turned on, right? So this will be connected. I mean, this VDD will be connected to this output. Okay, so the VDD will come to the output, right? So in this case, VDD will come to the output. So output will become 5 volt. So have you understood the operation? It's simple because the whole scenario is simple here because if we insert 0, then the NMOS is off and the PMOS is on, and output will be connected to the VDD. So output here VDD is 5 volt, and we treat it as what? Logical 1. Okay. So what is the summary of this operation? If we input 0, we are getting. If we input logical 0, we are getting 1 in the output. Isn't it like NOT gate? I mean inverter. If we input 0, we get a 1. But this is not one gate still. But we have not proved it yet. But to prove it, we have another combination, right? We have what is the function of NOT gate? We have to put if it gets 0, it will send 1 as output. And if it gets 1, then it should generate 0. We have not tested it yet. So let's test that. If we insert 1 as input, will we get 0 or not? So let's take that. So now in the next circuit operation, I will insert 1 as an input. Then what happens? I'm just drawing the same circuit. This is 0 volt, and this is VDD. So here I am in the previous case, we have inserted 0 as an input, and here we'll insert 5 volt as input, which is logical 1 actually. So don't get confused between logical 1 and voltage. So simply 5 volt means logical 1. So we have inserted 5 volt, logical 1. So let's analyze the NMOS. So the NMOS gate will get logical 1. So to simplify it, just take logical numbers. I mean zeros and 1. So if I get if we give 1, okay. So the NMOS gate will get what? 1 as an input. So NMOS will be on or off? On, exactly. So this will be and remember that this is our output. This portion of the circuit is our output. So here the NMOS will be connected, right? Everything on. So the output will be connected to 0. Let's talk about PMOS. So PMOS will also get 1, right? Because the same input is shared between NMOS and PMOS. So PMOS will also get 1. So if PMOS gets 1, then will it turn on and off or off? Off, because it's totally opposite to NMOS. So it will be off. So just erase this. This will be off and disconnected. Off means disconnected. So here, this is the complete operation. Here output is connected to 0, right? So what will be the output?
0.
0. This 0 will come here. Simply. Okay. So in the first case, the PMOS was on and VDD comes to output. I mean the 5 volt or 1 logical 1, whatever, comes to the output. And here NMOS is on, which is connected to the 0 volt. So output gets 0 here. And we know what is the summary? If we input 1, we'll get 0 output. And if we insert 0, we get 1 output. This is simply an inverter or NOT gate. This acts as an inverter or NOT gate, right? So this is how NOT gate is made using the MOSFET. Okay. So this is a circuit implementation. I mean the circuit level implementation of logic function circuit. This is we have NOT gate. Okay. Now let's move to another gate. So here it is the summary is written here actually. So this is a NOT gate. Okay. And this type of configuration is called complementary configuration. And because we have NMOS and PMOS, so if in a circuit there is both NMOS and PMOS, then we call, as you can see that the operation of NMOS and PMOS is complementary. I mean opposite. We are saying the same words, but same words. I mean complementary, inverting, not. Opposite, these are all same things. Okay, so in different occasions the different words are used. So yeah, these are the same things. So as NMOS and PMOS are complementary, I mean opposite or inverting operation, so that's why this kind of circuits are called in the this is in this circuit there is both NMOS and PMOS. So this is this kind of circuits are called complementary circuit. I mean CMOS, complementary MOS. So these are called CMOS circuits. Okay, so CMOS circuits are used in the computer. Yeah, I mean, so let's move to I think you will get you already get the outline. I have started with NOT gate. Next, I have started talking about in the previous. I mean, before the break, I have discussed NOT at different gates, right? NOT, NAND, NOR, AND, OR. So I will go one by one now, but you will understand the operation easily if I show you one actually. So let's move to the next gate, which is NAND gate. Let's see. Suppose let's draw a circuit here. This is ground or 0 volt, and these are two NMOS. And there are two PMOSes. And this is VDD here. Okay, and we will take the output from here. Okay. Now the input was this is VX1 and it looks complex, but when you understand the operation, it's very easy actually. So here there are two inputs, VX1 and VX2. Let's focus on VX1. Okay, forget about the the blue lines. Just focus on the red line. So here this is an input VX1. Where is it going? In this transistor, these MOSFETs are also called transistors because what is the full form of MOSFET? Metal oxide semiconductor field effect transistor, whatever. This time came from the working principle of this device. So MOSFETs are transistors actually. So whatever, VX1 comes here, and also VX1 comes to an NMOS and a PMOS, right? This VX1 is shared between an NMOS and a PMOS. Okay, and there is another input VX2 which is shared between another NMOS and another PMOS. Okay, so let's go through the circuit operation, which is very easy. Okay, so let's start with we have there are two inputs, so we will have combinations. We need to check all the combinations. Okay, so let's draw a truth table for this circuit. The first input is VX1, the second input is VX2, and we will measure the. Okay. Suppose start with x1 0 0. I mean 0 0. The both inputs are 0. Okay. So let's put 0 here. Let's put 0 here. So let's treat VX1 first. So if VX1 equal to 0, then what happens to this NMOS? So the gate of this NMOS gets 0, right? So will it be turned on or off? Off, because it is getting 0. NMOS, if NMOS gets 0, it will be turned off. Disconnected. So just if this is disconnected, just remove this. So there is no connection. Nothing here. Okay. And let's go to the PMOS. PMOS is also getting 0, right? This 0 is also going to the PMOS. So if PMOS gets 0, it will be on or off? On, exactly. Exactly opposite to the NMOS. So the PMOS is getting 0, so this will be turned on. So we will just turn on, which is connected. So there is a connection in this area, and there is no connection here. Okay, so we have analyzed VX1. Now let's analyze VX2. So if VX2 is 0, then this 0 is coming to this NMOS, and if NMOS gets 0, I mean this Vx2 is coming to this NMOS. See if Vx2 is 0, I mean NMOS is 0 get input, will it be on or off?
Off.
Off, great. So just remove this because this is off, nothing here, I mean there is no connection here. And this same Vx2 is going to the topmost PMOS, and the same 0 is coming here, right? Vx2 is, we have set Vx2 is as 0. So if it gets 0, will it be on or off?
On.
On, right? Because PMOS turns on when it gets 0. So there is a full connection between VDD to output, right? So there is a full connection between VDD and output. So this VDD, I mean the high voltage, which is suppose 5 volt, it's coming to the output, which is we can treat this as logical 1. So let me write this as output of the circuit. When we insert Vx1 equal to 0, Vx2 equal to 0, then we get 1 as output. Okay. So similarly, we have to actually go through all the combinations. So let's set next combination. Okay. So in the next combination, we have to check with 0 and 1. I mean, we have to set Vx1 to 0 and Vx2 to 1. Okay, let's do that. Okay, so let's treat Vx1 first. Vx1 equal to 0, it will come to this NMOS, and if it gets 0, the NMOS will be turned off. I have to erase it again. So Vx1 equal to 0. So the NMOS will be turned off, right? But there will be no connection here. And this same 0 will go to either all the zeros. So this same 0 input will go to this PMOS. And similarly, this PMOS, if the PMOS gets 0, it turns on. So it's connected already. Okay. And let's move to Vx2. We have set, in this case, we have set Vx2 1. Right? Okay. So we are setting Vx2 as logical 1. So this 1 will come to the input of this logic, I mean this NMOS. So when an NMOS gets 1 as an input, it will be turned on, right? So it will be connected. So this is connected. Okay. And we have treated this one, and if Vx2 is equal to 1, this same thing will come to the PMOS as well. Okay, so if PMOS gets 1 as input, it will be turned off, right? So if it's turned off, I am just removing this connection. So here, what will be the output? I mean, the output is connected to what? This is the connection actually. This is also already correct here. So VDD is not connected, right? Right? VDD is not connected. But VDD output is connected to, we have to analyze what output is connected to what? VDD or 0?
0.
So yeah, great. So we have definitely this is not connected to VDD because there is a disconnection here, but it is connected to the 0 volt. So out we will get 0 output. Okay, so let's write this here 0. Okay, so we have completed the second combination. We have 2 combinations more. We have 2 more combinations. So let's reset the circuit. There's a MOSFET here. Okay. So here we are in third combination where we will set Vx1 to 1 and Vx2 to 0. Okay. So let's analyze Vx1 first. So Vx1 is 1. So this NMOS, this one is coming to this NMOS and this PMOS. So Vx1 has come to this gate of this NMOS. So if NMOS gets 1, so it will be connected, right? So this will be connected. Okay. And the same one is going to this PMOS as well. So as this PMOS is connected to this PMOS gets 1 as input, it will be disconnected, right? For PMOS, if it gets 1, this will be turned off and this will be disconnected. So let me just erase that. Okay. And let's now analyze Vx2. So here Vx2 is equal to 0. So this Vx2 will come here. So this PMOS will get 0. So if this gets 0, it will be turned off. This will be disconnected, right? So this is disconnected. Okay. And this same Vx2 is equal to 0 will come to this PMOS as well. So PMOS, if the PMOS gets 0 as an input, it will be turned on, right? PMOS, opposite thing. So this will be connected. Okay. So now let's analyze. Output is connected to what? VDD or 0 volt? 0 volt, because so there is no connection between VDD because there is a disconnection here. So VDD is not connected here, but this MOSFET is turned on. That's why 0 volt will come to here. So we will get 0 as an out. Okay. So actually what is happening here, the summary of the operation, what is the summary of the operation? Sometimes output is connected to VDD, sometimes output is connected to 0. Okay, so these four MOSFETs, there are 4 MOSFETs, 2 NMOS and 2 PMOS. These are being turned on and off to make connections between output and VDD or output and 0. So sometimes output is connected to VDD, then the output becomes 1, then sometimes it is the output is connected to ground by these transistors, then ground 0 volt, then it is got then the output becomes 0. So actually these 4 transistors are controlling the connections between the output and VDD and the output and the 0 volt. And we have reached the last combination, which is 1-1. This is the last combination. So let me for the last time. So in this combination, the Vx1 and Vx2 both will be 1. Okay. So let's start with Vx1, which is 1 here. So this 1 will come. This 1 will come to this NMOS. Okay. This will be turned on and this will be shorted. Okay. And this same one Vx1 it's also going to this PMOS, the above PMOS, and the PMOS is also getting 1 as an input, and it will be disconnected, or this will be turned off. So there is no connection here. Okay, and let's move to the Vx2. Vx2 is 1 here, so this one will come to this NMOS, and if the NMOS gets 1, this will be connected, right? So this is connected. And the same Vx2 or x2 comes to this PMOS. I mean, the same one will come here. If it gets 1, the PMOS will be turned off. So there will be, so here is VDD, but this PMOS will be turned off. So there will be no connection here. Okay. So as you can see, the output is connected to what? 0. I mean, the ground or 0. Okay. It's not connected to VDD. Okay. Output will be 0. Yeah, so these are all the combinations. So what is the target? So what did we make? Okay, so this is our truth table for this circuit. But let's match this truth table with the common gates we have. So what is the output? I mean, what are the output for this combination? 1 0 0 0. Okay, so let's move to the gate truth tables of the gates. Here the first should be 1, the first one should be 1, and the other 3 will be 0. So which truth table is matched with that?
NOR.
No.
NOR.
Question.
Oh, yeah. So we get from the circuit analysis, we get this output, right? 1 0 0 0. Okay. So 1 triple. So this out. So yeah. So for which truth table matches with that truth table? I mean, we have actually devised. I mean, we have created a truth table.
Last one. Okay.
Yes. So as you can see that the last one matched with the truth table, and this is for NOR. Okay. So what did we do? We just made a NOR gate using MOSFETs. Okay. What did we do? We just made a NOR gate. So we have done this. So this is a MOSFET. I mean, transistor level circuit. I mean, with this circuit, we actually make NOR gate. Okay. In the same fashion, I think you will be able to do this for all the gates. I mean, the other gates circuits are already given in the slide. Like this is NAND gate. So I'm not going to show that because this will be repetitive. You already get the idea, basic idea. You can just match that. You just for practice, what will you do? You just remove this table. Just forget this table. Just take this circuit and complete the truth table, and you will see what is the output and will it match with the? I mean, does it match with the NAND gate output? I mean, NAND gate truth table. You can do that. Okay, so you have to go through the combinations as I've shown you. So 0 0 0 1, all the combinations, and just take the output, and you will see that this circuit output will be matched with the NAND gate. You can check. You can check in your home. So for practice. So this is a NAND gate implementation. This is NOR gate which I have shown you, and why? Okay, so to make AND gate, so we have shown an AND NOR, and suppose we have shown you NOR gate. This is NOR, right? Let me let me draw this circuit in a fresh set. It will be very quick. I mean, I'm just drawing the circuit again. Okay, so simply this is the NOR gate that we have shown. I have just read on this circuit here. So this is NOR. So what we have, I have told you that from where did we get the concept of NOR? We have told you that the opposite of OR is NOR, right? Okay. So from OR, if we invert the OR output, we get NOR. In a similar fashion, if we invert the NOR, what should we get? OR. Yes. So we should get OR. Surprisingly, the weird issue, the weird fact is that the NOR gate, making NOR gate using MOSFET is simpler than OR gate. Do you get that? Let me repeat that. So this was a circuit implementation of NOR gate, right? This is very simple, but OR gate is complex, more complex than this. Not very complex, but NOR is making NOR using MOSFETs is simpler. And to make OR, what should we do? I mean, this is NOR. Okay. So, sorry about that. Oh, yes. So I'm not sending someone. Okay. So do you have access?
Well, we have access to each other.
Oh. Okay. So sorry about that. Yeah. So okay, this is NOR, right? So how should, as I have told you that OR is the inverted operation of NOR. Okay. So from NOR, how should we get OR? We need to invert it, right? Exactly. So we have already shown you an inverter. At the first place, at the first circuit, we have shown you as an inverter, right?
Not gate.
Yeah, not get or inverter. So what if we have? I'm representing this NOR circuit as a block, maybe to simplify. So this will give me NOR, and if we add an inverter after this, what should we get? OR, exactly. So this is how OR gate is made actually. So they put an inverter at the output of the NOR gate, and then they get OR. That's how OR gate is made. But OR gate logic, I mean, OR gate is simple. Just you have to add. But it's simple to think and it's simple to calculate. But in terms of circuit implementation, NOR gate comes first, then OR gate. Okay. So yeah, then let me show you the OR gate circuit. It looks complex, but when you understand, it's very simple. This is not very OR. It's not showing. I just somehow I missed. Let me show you for me. Somehow I missed the audience. Let me pause for it. As we have and get, so let's try with that. Maybe. Okay, so in a similar fashion, to get and get, so to in a similar fashion, actually, making NOR gate, making NOR gate is simpler. I have told you. In a similar fashion, making NAND gate is simpler. Okay, instead of AND. So how should the NAND gate looks like? So as you can see, I'm just drawing the NAND gate first. Let's draw the NAND gate circuit structure. This is NOR gate circuit structure. NAND gate circuit structure is like this. This is MOS, and there are two MOS, PMOS. This is PDD. So we will place them side by side so that we can compare them. I mean, NOR and NAND. NOR gate and then NAND. NAND. Okay. So let's focus on this portion where there is only NMOSes, and here as well. Let's focus on the cycle. How these NMOSes are connected? I mean, series or parallel? Parallel, exactly. This is parallel connect. Okay, and in the NAND gate, it's connected in series. So, do you remember that? Or is related to parallel and addition operation. I mean, let's write this plus. So these all are connected, or parallel plus. So if so what is the realization here? If we connect two NMOSes in parallel, we should get OR, right? But here we are just getting the inverted version of OR, which is NOR. Okay, so that's how CMOS, I mean complementary MOSFET works. So this is you will get here NOR. So to just simply invert this, I mean to get from to get OR from NOR, you have to just put an invert, and you will get the OR output. So and for NAND, as you can see, this is there are series. The NMOSes are connected in series, right? So series connection is related to AND operation, and this is also related. Sorry. This is series connection, and this is multiplication operation. Okay, so yeah, and this is so we from this circuit actually we got the inverted value. I mean this is I mean we get NAND, and from here if you want to get AND, you just need to add an inverter. Okay, then you will get NAND, and you can see, you can observe another thing. Here, the NMOSes are connected in parallel, but look at the PMOS network. They are in series because they are weird, right? So, I mean, they're complementary to NMOS. I mean, if the NMOS is connected in parallel, they will be connected in series. They are totally opposite. Okay, and look at the NAND circuit. Here, the NMOSes are connected in series, so the PMOSes will be connected in parallel. So actually this is complementary network. So we can represent this kind of circuit like this. There will be two blocks. The below block, I mean the lower block will be NMOS network. NMOS network, and the upper block is the PMOS network. In the upper block, there will be only PMOSes, and in the lower block, there will be only NMOSes, right? And now, if I so let's write the value directly here. So if they are connected in parallel, we have told you that we have shown you, actually we have proved actually this output will be a NOR output. We have proved, because we have to use the truth table. We have inserted all the combinations and check the output, it matches with the NOR. So we at this point we are convinced that this here output will be a NOR output. So how will we represent NOR as a function? Like here Vx1 and Vx2 are two inputs. So how do we write NOR? We at first we write OR, then we put a bar over it. That's how we write NOR operation. Okay, so this is NOR. So we get x1 plus x2 bar here. Okay, and in this case, what do we get? We have not proved it yet, but the proof is shown in, for the. I mean, this is simple. So if you just analyze all the combinations and match the output, you will see that the output of the circuit will match with NAND truth table. So we should be convinced that this is NAND. So how do we write NAND? At first we write x1 dot x2. And then we put a bar over it. So when we write, then we actually write AND first, the AND or first, then we put a bar over it to get OR and AND. Okay, so and from this idea, I think you can do it. If here x1 plus x2 bar, if this circuit is implementing x1 plus x2 bar, let's focus here. But if we want to make x1 plus x2 plus x3 bar, is it possible to make? So here in this circuit, two inputs, x1 and x2. So there were two NMOSes, right? So using the same idea, we can just implement this for infinite number of inputs. Let's stick with 3 inputs. So what should I extend in this circuit to get this output? Any idea? So here we have this is x1 plus x2 bar, right? 2 inputs. Okay, so to handle 3 inputs, we will be needing 3 transistors, 3 NMOSes, and all of them will be connected in parallel, right? Exactly. So just simply we will connect another transistor here in the same way. So this just we have to attach another transistor, and in a similar fashion we have to do this for PMOS as well. So in the PMOS network we have to add another transistor in series, because what will we do in NMOS cases? The opposite we will do for PMOS network. So we will add another PMOS right here, and we'll insert x3 or Vx3, whatever. So we can do this for infinity number of inputs, right? So if there are 4 inputs, we will just attach 4 NMOSes in parallel and 4 PMOSes in series, right? That's how it works. And for this one, this is for x1 dot x2 bar. So if we want to get x1 dot x2 dot x3 bar, what should we do? Yeah, we have to connect another NMOS in series with this, and another PMOS in parallel with this. Yeah, that's how we will get 3 input NAND gate. Okay, so these are 3 inputs. So this circuit will be called, if we use 3 NMOSes and 3 PMOSes, this circuit will be called 3 input NAND gate. Okay, and from an NAND gate we know that from NAND gate we can get AND gate. That's by just inserting a NOT gate here, we will get the AND. Okay, so if we can make an AND, we can easily make AND. Okay, and if we can make NOR, easily we can get OR by just inverting this. But the inverting operation is nothing. Okay, it's very simple, but the main idea is NAND and NOR. So that's how, using NOR and NAND, you can make AND or whatever and any other function. Okay, so that's why NOR and NAND are called universal gate. So let me write this because this is very important. So NOR, but because using NOR and NAND, you can make any function. Okay, so and this is called universal. These two are called universal gate. Yeah, but you can argue that why and or are not universal, because and or comes from, can be can be made from NAND or NOR. So the building block will be NOR or NAND, right? So the NAND and NOR, using NAND and NOR you can make any gate, and or whatever. So that's why they are called universal gate. Okay, and yeah, so you can right now you can make any function, right? Okay, so to summarize the whole idea, maybe at this time you are confused between gate level scenario. I have shown you gate symbols, I have shown you MOSFET symbols. So what are the connections between them? Let me clarify that. Suppose let me I think this is the summary of today's class. This will be the summary. Suppose you have to make this function. I have shown you how to do this using gate. So if I think the confusion will clear here. So if there is any, suppose I need to do this operation. Okay, so suppose in any application we have to do this operation. So how will we make the circuit? At first, we will the simple. I think you have already get an idea that this MOSFET level. These kind of circuits are looks too complex. Okay, but at first, what we do some gate level analysis first. So we do. Let's go back. We have to do addition operation. For addition operation, we will have OR gate. So we will have x1 and x2. We have done this already in the first part of this class. So for this portion, to implement this portion, we need an OR gate, which will take x1 and x2 as inputs and will give you, OR gate will give you the addition operation. Okay, and this x1 plus x2 should be multiplied with x3. This circle and this circle should be multiplied. So for multiplication operation, we will need AND gate, right? So we'll take an AND gate and take x1 plus x2 as an input, and the another input is x3. So the AND gate will just multiply them. Multiply the two inputs. The first input is x1 plus x2, and the second input is x3. So this thing is called gate level analysis. Okay, but here there is no transistor shown. Okay, so there are several levels of circuit design. Okay, so this is called gate level, because I have shown here just only gates. Okay, but how this gets will be implemented? But I have told you that I mean, for a building, the brick is a building block, right? I mean the smallest unit. Where for circuit design, I mean for microprocessors and memory, the smallest unit is the MOSFET. Okay. So this is a representation, but we have to also draw what's inside this gates. We already know that how to implement OR gate. Okay, so we will just take this circuit, these circuits. I mean, suppose inside the OR gate, what is inside the OR gate? There are several MOSFET, I mean NMOS, PMOS, whatever. Okay. Finish this. What I'm drawing is just simply an OR gate. So, something like this. So inside the gates, there will be transistors. When you draw the whole circuit using the MOSFETs, then this circuit will be this representation will be called transistor level. When you will represent all the gates in terms of transistor, I mean what's inside the transistor, you have to draw also. Okay, so that's how this is called transistor level. So actually, we as different engineers actually works on different segment, because everyone cannot be an expert of transistor level. So because wire distribution, right? You have suppose you have functions. So someone will convert this function to gate level, and someone will convert this gate level to transistor level. But yes, I'm doing this manually, but there are some softwares, okay, where if you insert this function, this kind of function, it will generate the transistor level circuit. There are some automated softwares. One popular software, whole industry uses it, which is called Cadence. Okay, so Cadence, you can give Cadence the function. It will, if you want, I need gate level implementation. Then the Cadence will generate you a gate level implementation. If you need transistor level implementation, the Cadence will give you the transistor level implementation. So yeah, because this is simple function, we can draw it manually, I mean with hand. But as I have said you that real computers deals with there are three variables here. I mean 3 inputs, x1, x2, x3 in this example circuit. But in real life computer, there will be billions of variables, billions of x's like this. So we cannot do it manually, right? So that's why software is used, which is I have told you that Cadence. You will have a project in VLSI. Oh, and this type of designing is called VLSI, very large scale integration. VLSI. This is a big field. Okay. Using VLSI, actually, your chips, I mean, the chips inside your computer, chips inside your mobiles are built using VLSI. I mean, this type of analysis is called very large scale integration, which is, in short, it is called VLSI. Okay. So you will learn Cadence. Okay. So in Cadence, you can, I mean, you can do anything. I mean, you can do the transistor level analysis. Suppose you have a function, you can draw this kind of circuits inside Cadence and analyze it something. And you also can draw gate level analysis. Okay, so whatever. I think you got the main idea how computers work, right? I mean, how computers are made. Okay, this is the sole idea. This is real life. Okay, but I mean, this is how chips work. Okay, so they implement thousands, millions of functions, and these are implemented using MOSFET. This is how they are connected actually. So let's move back. Okay, we'll yeah, this later. I think you will work with this. I mean, how will for prototyping purpose? There are chips in the market which have some NAND nor I mean not which can do this kind of operation. So as you can see, this is a chip. Inside the chip, this is the layout of the chip. I mean, this is called pin diagram. Okay, let me draw. This is a picture of a real chip. If you buy chip, you will this will look like this. Okay, so this is a chip for NOT gate operation. I mean, inside this chip, you can do NOT gate operations. So inside a chip, there will not be a single inverter. A single inverter. As you can see, there are some pins where you can connect. Okay, these are you can call it as terminals. Okay, so there are two sides. In one side there are several pins, and on the other side there are several pins. Like here, there are 1, 2, 3, 4, 5, 6, 7. So I don't think this is the correct representation of this specific chip, because NOT chip will have 1, 2, 3, 4, 5, 6, 7. 7 pins this side and 7 pins on the other side. So there are two lines. Let me just draw something. The chip looks like this, the NOT chip, NOT gate chip. Or whatever, some numbers of pins. Okay, so this pins has this chip has pins in two sides. Okay, that's why this kind of chips are called dual inline package. Here you can see the name of this kind of chips are dual inline or deep package. I mean DIP, dual inline package. But there are several other chips that will have pins in all the sides. So, but the NOT gate and the gates have two sides, but there are several chips where you will have pins in all directions. Okay, so yes, but for this gate, I mean this NOT gate, and the chips are called using some code names. I mean some code numbers like 7404. It's the chip number, I mean model number for NOT gate. And for 7408, I mean for NOT gate, the chip number is 7408. I mean there's a chip like this. Okay, but you how do you know that this is NOT gate or AND gate chip or OR gate chip? So the model number is written over this, I mean above this area, so that you can get an idea that what chip is this. So this is for I mean if you do electrical engineering in your BSc, you will have to do projects using these chips. Okay, so these chips are very, I mean, cheap. I mean, not expensive. Okay, so yes, so if you do electrical engineering in your undergrad, you will have to use these gates, and I mean these are gates, basic gates. So you have to remember. I mean, you will have to remember the chip name, because they will be mixed inside a box, and you have to find them one by one, which gate is what. So you will remember the number. So whatever. Right now, you do not have to remember any number or anything. So for NOT gate is 7404, and AND gate is 7408 and 7432 for OR gate. As you can see, let's look inside the NOT gate. There is not a single NOT gate. In a chip, they provide several NOT gates actually. As you can see, 1, 2, 3, 4, 5, 6. In this package, there are 6 NOT gates. I mean, in your circuit, you may need to use multiple NOT gates. Then you can use this chip actually. So to get, as you can see, the pins are actually numbered. Here numbers is missing, but yeah, the pins are numbered. Suppose this pin number is 1, this is 2, this is 3, 4, 5, 6, etc. And when you connect them in the circuit, you need to see, this is called pin diagram. This one, the below picture is called pin diagram. And if you need to connect, suppose you need to use one NOT gate, so you will use, this is pin number 1. So let me. Okay, so this is pin number 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. Numbering done like this actually: 1, 2, 3, 4, 5, 6, then anti-clockwise. 8, 9, this is 10, this is 11, this is 12, this is 13, this is 14. Okay. So if you need one, I mean, this is one input. Suppose this is x1. You need to invert it. So what will you do? You will connect this x1 to pin number 1. Okay, and from where you will get, from which pin you will get the output? 2. Yeah, because as you can see, the pin. This is why pin diagram is important, because you do not. Practically, the chip will look like this. Okay, this NOT gates are written in the pin diagram, but it will not be shown in here. Okay, so you have to keep this in mind. I mean, when you make connections, you have to know. I mean, you have to keep this. I mean, you do not have to memorize, but you will have this pin diagram. If you search on the internet 7404 pin diagram, this will show up. And from this you can just connect them. So if you need to connect something, I mean, if you need to invert x1, you have to connect this to pin number 1, and you will get the output from pin number 2. So the pin number 2 output, what will be the pin number 2 output? Because this is a NOT gate, the output will be x1 bar, right? X1 bar. So if you insert 1 at pin number 1, x1, and you will get pin, x1 bar from pin number 2. Okay, that's how you can use the multiple pins. Okay. And see, in a similar fashion, the NOR gate and AND gate, OR gate are also made like this. This is pin number 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and so on. This is 8, then.
Always 7 inch.
Sorry?
Always 7.
For this series, I mean, this is called 7XX series. I mean, this is for this series. There will be 7 pins one side and the 7 pins in the other side. Yes. But there are other chips and chip series as well. There will be different number of pins. For this series, this is called 7XXX series. For this, and maybe I don't know how these numbers comes, but right now I am assuming that the 7, this starts with 7, because there are 7 pins on one side. Maybe, I'm not sure. Don't put me on that. Maybe. So these are some numbers. Okay. So so how will we connect these pins? Suppose we need to multiply x1 and x2. What will we do? We will take x1 and connect it to pin number 1, right? And we will take x2 and connect it to pin number 2, because these 1 and 2 pins are, look at this. This is AND gate, and these are the inputs. Okay, 1 and 2 are the inputs here, and you will get the output from pin number 3. Exactly. So what will be the output? This is AND gate. So AND gate will simply multiply the input. So you will get x1 into x3 from pin number 3. Okay. So that's so in this package, as you can see, there are 4 AND gates. So if in your circuit you need 4 or less, you will need 1 chip. Okay. So but suppose you are implementing a function that requires 5 AND gates, then you need to by another chip, right? Okay, so and another thing is I have not told you about other pins. Maybe where it is. Yeah, two other important pins are here, which are pin number 7. Look at pin number 7 and pin number 14. What are they? The pin number 7 is ground, and pin number 14 is VDD. So to run this gate, you need power supply. Okay. This 1 and 2, these are inputs and outputs. These are not power supply. To run this gate, I mean to function it properly, this chip needs power. To power up the chip, you need to connect VDD and ground. I mean, what is VDD? What will connect to VDD? Yeah. So suppose in practically we have batteries, right? So we have batteries. We have to connect the positive terminal of the battery to the VDD, and the negative terminal of the VDD, battery to ground to power up the chip. Okay. Yeah, it happens. In our undergrad, we actually did this mistake. We just connect inputs and outputs and forget about the powering of the chip, and the circuit doesn't work. Okay, so you have to remember that you have to connect, or you have to power up the chip. Otherwise, it will throw errors. I mean, it will not work. The chip will not work if you do not connect the the VDD and ground pins. Okay, so yes. Okay. We can simulate this in a Tinkercad as well, but I am thinking that is necessary because you already have understood the idea, right? Do we need more proof? If we need more proof, then we go to the simulation. Okay, so yes, maybe not simulate. Let's talk about instead of simulating this in Tinkercad. Because we will be using Tinkercad more in the project. Let's talk about the project. I think you will have to do 2 projects.
Each of us.
I think for the hardware project, because in the hardware project we will be dealing with a microcontroller which is called Arduino. I think some of you have heard about Arduino. Yeah. So we will be using Arduino to do some project. Let me give you. So okay. So what is the overview? So we will have 2 projects. One will be with hardware, and the another will be with software, which is for the hardware project we'll also have to do some software, but that's a different thing. But your target for this this program is to design a chip. Okay, so for chip design you will be using Cadence, maybe, because Cadence is a very expensive software. You cannot just download and install it. It's very expensive software. Usually the universities buys it and give access to the students. So we do have access, and we are trying to get access for you as well. Okay. So we are in the process, but it will be after the break. I mean, there is a break in December. So after the break, maybe we'll manage access to the Cadence. I mean, it is a very expensive software. So and we'll try to give you access to Cadence. And that's after the break. And before the break, we want to finish the project, the hardware project. Okay. Let's talk about the hardware project. So in the hardware project, we'll be using a microcontroller Arduino, and simply what is at first, what is Arduino? Arduino is just a simple microcontroller, and you can tell it as a small computer. And let me show you the picture of that it will, in that way it will be easier. We'll try to use Arduino Mega. This is an Arduino. Okay. As you can see, there is this chip embedded here. This is a chip, and as I have told you, there are pins in all sides here, not like the AND NOT or AND gate. This is a chip, and there are pins in all sides, like in all directions there are pins. So this is this kind of, you can tell this green board. Sometimes it's green, sometimes it's blue, whatever. So this board that holds all the chips and other components, this is called, you can call this as motherboard. You have heard about motherboard inside your computer, right? So motherboard, the names are explains it all. Actually, this is motherboard. So it actually holds all the components like chip and other input and output pins and etc. Okay, so so where these are the pins actually. You can connect wires from outside to these pins. Okay, so what does this Arduino do? It actually implements the functions that we call, it can implement any many functions. Okay, like this, we have told you that x1 plus x2 dot x3. This is like a computer, so it can take input and gives you some outputs. Okay, so there are and this is very popular for robotics. This is very necessary component for robotics. We use microcontrollers. I mean, this kind of microcontrollers. There are other microcontrollers as well. This is very popular, and other microcontrollers are called some Raspberry Pi. There are other microcontrollers, but we will be dealing with this specific microcontroller, which is Arduino, and there are several versions of Arduino. There are several versions like this is the, I think this is the biggest one, right?
Okay.
This is the biggest, right? So this is the biggest version of Arduino, which is Arduino Mega. Then there is a smaller version, Arduino Uno, and then other smaller version, Arduino Micro, maybe whatever. Yes. So based on different size, there are different versions. The difference is very small. The difference is the as you can let me draw it maybe. So the very small version of Arduino is called Arduino Micro. The bigger version is called Uno, and the biggest version is called Mega. I mean, why we will choose Mega? Because Mega has suppose I think let me, I do not know exactly the number of bits. Let me search for it. The number of, I mean, it's obvious. Let me just tell it in a general way. So Mega has we need many input pins. Okay. So we need many input pins. So Mega has the highest number of input pins, and Uno has a smaller number of input pins, and Micro has the smallest. Okay, so we actually need many input pins. So that's why we will be choosing Mega. If you need many input pins and many output pins, then you have to choose Mega. In our case, in our project, we will be needing 16 input pins. I will describe the project later, but let me tell you the requirements. We will be needing 16 analog input pins, but Uno does not have it. Okay, so for getting 16 input pins, you have to go to Arduino Mega. That's why we will be choosing Mega if possible. So so for this hardware project, we can make groups because we'll be needing hardwares. Okay, so that's why, and the project may be may need more work. So it will be best to distribute the work between the group members. So yeah. So what will we do this? So using Mega, so according to how many pins you need, we will need 16 pins. If you need less number of pins, we could have used Uno. Okay. So we will be dealing with photodiodes. Have anyone heard about photodiode? Photodiode. It's a sensor. Okay. It's a sensor. For what does photo means? Light, exactly. So light. So it will sense light. Simply, it's a photodiode. Will sense light. Suppose this we treat this as a box. So when light falls on photodiode, it generates an electrical signal. Okay. Depending on the illumination, I mean, the light can be dim, the light can be bright. So the theory is when the light is dim, sorry.
It's not like UV light or anything, just natural light.
Yeah, that's a good question. There are different photodiodes. Some photodiodes captures only visible light. Some photodiodes capture infrared. Some photodiode captures UV ray. It depends. It depends on the application. If we want to capture visible light, we will be using the photodiode that captures the visible light. But for defense applications, if you detect, if you want to detect something in the air, okay, so sometimes this signature, suppose there is a fighter jet, you want to detect that. Sometimes it will be easier to detect when the fighter jet goes through the air, it will actually heat up the air, and there is a thermal signature. Okay, so that can be detected using infrared, and sometimes that is easier to detect the infrared. So they use infrared camera. So what does infrared camera means? It will take infrared that we cannot see. We cannot see infrared. Okay, and even in the forget about the jet fighter, whatever. In the when the lights are off, when it is dark, okay, we cannot see, right? But there will be radiations. Infrared or thermal signature. How does camera see? There are thermal cameras. How does camera see? Then when this is dark, our body generates heat. Okay, and that actually creates radiation. Not radiation actually, electromagnetic waves, and that is captured by some photodiodes. Okay, so there are cameras that can see in the dark. Why we cannot? Because that photodiode can capture the infrared waves, but we cannot see that. So there are different photodiodes actually that can capture different levels of light. Not levels, different. The lights are. Infrared. What is the difference between infrared and visible light? Their wavelength is different. This is all physics actually. So their wavelengths are different. So whatever. So, the summary is there are photodiodes which can capture visible light, and there are other different photodiodes that can capture infrared. That other photodiodes can capture UV and other spectrum. So, but we will be dealing with visible light. Okay, so the photodiode will be using that will be dealing with visible light. And what is the main function? Working principle of the photodiode. If there is low light, then the electrical output signal will be low. The voltage will be low, like 0.1 volt. I'm just taking an example. And if the light is brighter, then the voltage will increase. If we plot the graph like this, with light intensity, with light intensity, the voltage will also be increased. I mean the electrical signal, which is a voltage. So okay. So yeah, this is this design in a way that with increasing light intensity, the voltage will be increased. So we from using Arduino, we cannot measure light directly because Arduino or microcontrollers, these are chips. They handle voltage and currents. So they cannot measure. Arduino cannot measure light or something or any signal. Okay, so there are some sensors. What are called sensors? Sensors are sense different physical signals like light and convert it to electrical signal because we will be because we can process the signal we can process electrical signals in microprocessors or microcontrollers, not light signal or not a sound signal, whatever. So what are the sensors? Sensors simply takes physical signal like light, like sound, and it converts to electrical signal. Sorry?
Temperature also can.
Exactly, temperature. Yeah, it senses temperature and converts it to electrical signal because the processors, the chips, or computers, or mobiles, or whatever the chips are, they deal with electrical signals. Okay, so you have to convert the physical signals to electrical signals so that we can process it in the microcontroller, microprocessor, or whatever, because they deal with voltage or currents. Okay, so sensors are like that. Temperature sensor, sound sensor, light sensor. Like photodiode is a light sensor. Okay, so photodiode. There are other light sensors like photodiode, phototransistor, and other things. And and camera is a kind of sensor, right? What does a camera do? Camera actually there are photodiodes inside the camera. Many number. I mean, inside a camera, there are suppose you heard about resolution, right? Suppose what is the which kind of resolution number you have heard about it? 1920 cross 180 pixels. So what does it mean actually? Yeah. So for a camera, I'm not talking about display. Display is a different thing. The display actually the display converts electrical signal to optical signals. I mean light signals. Suppose this is a display. It is actually taking electrical signals and converting it to optical signals. This is opposite. Display is the opposite action, and camera is the opposite. Camera takes light signal and convert it to electrical signal, and display takes electrical signal and converts it to like optical signal. I mean light signal. Optical or light is same thing. So I'm talking about camera. So if a camera resolution is 1920 cross 1080, as they actually represent this as megapixel, right? 48 megapixel camera. Okay, so actually I have a video about this, how a camera works. If you go to the Nordic Lab, where your recordings are uploaded, in that channel I have a video where I have shown how I mean the basic working principle of a camera. Okay, so suppose let's deal with a small number to easily understand. Let's forget about mega. Let's suppose we have a camera of 400 pixels. What does it mean? 400 pixel means there will be an array of photodiodes, because not a single photodiode cannot take the whole picture. Okay, so to capture the whole picture of a scene, we will need an array of photodiodes. Okay, there will be so 400 pixel can mean that you have 40. I mean one. This is one photodiode. This is another. The squares here are photodiodes. Suppose there are 40 photodiodes in this line. I cannot draw all the 40. And like this, we have, suppose we have 40 photodiodes, and we have 10 lines of them. I mean, this is 10 lines of them. So total number of photodiode, what will be the total number of photodiode? 400, right? So you have to just, there are 40 number of columns and 10 number of rows. So if you multiply 4 and rows into columns, then you will get the total number of the photodiodes, which is 400. So it will be a 400 pixel camera. Okay. And so suppose someone is telling you this 48 megapixel camera. What does it mean then? Let's like that. 40 megapixel camera, iPhone 16, 40 meg. I'm not sure iPhone 16 is 48 megapixel or greater. I don't know. So whatever. 48 megapixel camera. What does it mean? It means you have 48 mega means million. So 48 million pixels are there inside this camera. Pixels means photodiodes actually. In every pixel there is a photodiode. So 48 millions pixel. Suppose so I mean there is an array with number of rows, some number of rows and some number of columns. If you multiply those number of columns and rows, you will get 40 million. So there are 40 million pixels inside a photodiode. Inside an image sensor chip. I mean, these photodiodes are arranged in a chip, which is called image sensor chip. Okay, so if you go up, you will actually integrate more number of photodiodes inside a camera actually. So we will try to mimic that. We cannot make 48 megapixels, right? But we can have a mimicry of camera maybe, because you know that if we need to make a photo, I mean camera or image sensor, you will need photodiodes. Okay, so what I was talking, that camera, so there is a difference between camera and display. So camera takes light as an input and generates electrical signal. And have you heard about beats and bytes? Of course you have heard. So the beats and bytes, do you know what is beats? Suppose beat. What can be the value of a beat? You know, 0 or 1. It's connected to Boolean algebra. Okay, so yeah. So beats in one bit means the bit can save 0 or 1. The value of bit can be 0 or 1. Okay, so this is called bit. And what is byte? 8 bit. If you have 8 bits, suppose 1, 2. This squares are 1 bits. 3, 2, 5, 6. So these are bits. So if you have 8 bits, then it is called 1 byte. Okay, so this is nothing but zeros and ones, bits and bytes. So and these are electrical signals, zeros and ones. So bits and bytes are electrical signals actually. That's how the signals are saved. Okay, so light signals, camera takes the light signal and convert it to electrical signals or bits or bytes. I mean, electrical signal is equal to bits and bytes. So it saves in a memory, and maybe yeah, it saves in a memory, or it can live display. I mean, it can show in the display. So the display is the opposite. It takes electrical signal. I mean, suppose there are processors that is generating. Let me draw the whole picture maybe like this. So not like this, but a camera maybe. As you can see, there is a camera, right? Okay, it's not showing. So what is it doing actually? So suppose there is a camera and this is converting light signal to electrical signal. And this is either it can be saved in a memory or it can be processed in a processor. In this case, this is processing. This is being processed in the processor because it comes to a computer, and then it is saved in electrical signals. I mean bits and bytes. Electrical signal, and then from this electrical signal, suppose this is a processor, and this is a display. And display takes data, I mean the electrical signal from the processor, and it converts it to light signal again. Okay, the output you are getting, these are all, and inside the display there is pixels as well. Okay, so it is getting the data from the processor and generating the light signal or optical signal or display. Okay, so that's how actually the processor works, maybe the sensor and processor, because this is all connected actually. So the processor is integrated with sensors and displays. In this case, the light is the input. I mean, this is sensing light and this is also displaying light. Okay, so inside the why, and you can question this, why electrical signals? Because as I've said, the processor deals with electrical signals, bits or bytes, and why not other signals? Because you can control electrical circuits. I mean, the electrical circuits can go down to nanoscale level. Any other signal, any mechanical signal cannot go. I mean, mechanical system cannot go to that small scale. So you can do many operations. I mean, whole host of operations. I mean, millions of operations inside a microprocessor, and that the microprocessor and memories they deals with electrical signal. That's why every sensor, I mean, most of the sensor does this. I mean, takes a physical signal and converts it to electrical signal, not other kind of signal, not mechanical signal. It converts it to electrical signal. Okay, like the temperature sensor, it sends temperature and convert it to electrical signal. And yeah, in your home you have the AC actually. I mean, the air condition controls the temperature. It actually takes. It has a sensor. And how does it know that you set 72 degree Fahrenheit? Suppose, how does it know that it after reaching to 72 degree Fahrenheit it stops, right? Because you have set 72, but if it continues to work on, it will go beyond 62. Suppose, okay. So how does it know it's 72? Because it has a sensor, temperature sensor. So it analyzes the temperature, and it also shows you in the display, right? The temperature is now like this. So the display actually here in this case, the temperature sensor is converting the temperature to electrical signal, and that is inside the display there is a chip. Okay, that deals with processing. So that takes a temperature sensor signal and convert it to electrical the sensor, and then the electrical signal is processing processor, and it shows you in the display, and it controls the other mechanism to stop the AC. You can do anything. I mean, if you can convert this to electrical signal, then with the processor you can do many things. So that is the target of the sensors, to convert the electrical signal, other signals to electrical signal. So let's go back to our project. So our project is to use photodiode, which is a light sensor, and we will make an array of photodiodes. So we have we will do it with I mean, we are not using very large scale integration. We have limited number of photodiodes. So we will be designing a 4x4. What does it mean? So there will be 4 rows and 4 columns. So we'll make this kind of array, photodiode array. So this is called 4x4 because the number of rows are 4 is 4 and the number of column is also 4. So there will be 16 total, 16 photodiodes. We'll be making a array of photodiodes like this. I mean, we are trying to make a camera, a small version of camera. Then what will we do? We have 16 photodiodes, and we will take this the signals of each photodiode to a microcontroller, which is Arduino Mega. For processing the signals from the sensors, we will use Arduino Mega. Okay, so we will take each and every photodiode's output to an Arduino. So, so deal with all the 16 photodiodes. How many input pins this Arduino should have? 16, right? That's why I have told you that we will be using Arduino Mega, because Arduino Uno, the smaller version of it, does not have 16 pins, input pins.
How many Mega has?
16.
Yeah.
I think it's 16. Let me just double check that. I checked yesterday. 16. I mean, I didn't. Sorry. How many input? No, it's in this. But, oh, 54 digital input output means I'm not going to use digital pins. It's actually the total number. Yeah, here as you can see that Arduino Mega 23560 model has 16 analog inputs. So we will have to deal with analog pins. Okay, so we will be needing 16 pins, and the Arduino Mega has 16 pins.
You're gonna give it to us, right?
Yeah, exactly. Okay. And what will we do with this? Okay, so we will take the input. Why are we taking analog pins? The first question is because the sensor will be giving us analog outputs. What is analog and digital? As I have told you in at the very first moment of this class, the digital means zeros and ones. But in this case, we will have to deal, because the photodiode will not give me 0 or 1. It will, depending on the light intensity, it will give different values, right? 0, 0.1 volt, 0.2 volt, 0.3 volt. So that's why we will need some analog pins. And digital pin, what does digital pins do? It will take an input and it will give 0 or 1, nothing between. But we have to measure, because depending on the light sensitivity, the scene will be different, right? Every point of the scene is not at same intensity or in between 0 or 1. Different levels of intensity. I mean, different levels of light inside. In a scene, there are different levels of scenes, right? Okay. I mean, different by different level, I mean the brightness of each point in a scene is different. So yeah, that's why we will be needing analog input.
So your input and output is changing then, depending on the light.
Exactly. Yeah. Depending on the light, here light is the input, and depending on the light level, the output will be different in different levels. So after getting those inputs, we will and this Arduino Mega will be connected to control this, because Arduino Mega is a small computer. It does not have any display. So to control this Arduino Mega, we will be connecting this to a computer. I mean, any computer can be connected to the Arduino Mega via the USB port. The Arduino Mega has USB port, so we will do some coding. So this will involve some coding as well, because to control this Arduino, what will we
The computer acting as a display board.
both as DisplayPort and as I have said that this should be this will not work on its own. We have to send commands to the Arduino. What will it do? It will take signals. Then what will do? What will it do? It will actually and we will send codes using computer, because we have to write code inside computer, and then we have to send the code to the Arduino. Uploading code to the Arduino is called burning. This time is called burning the Arduino. Maybe this is burning the Arduino means I am uploading. I have done some coding. The coding language is very simple. Are you familiar with any coding language?
Python.
Yeah, it's like Python or maybe it's easy, very easy, but not like Python is you can do very complex things in Python, but this is very simple, just sending signals like that. I'll show you. I cannot show you in this class, but in the next class I will show you how to code in Arduino. Maybe you have to download a software which is it's free software.
Any laptop can work.
Yeah, any laptop.
That is our next class. We're doing the coding.
It's a task of project. We have not decided yet that we will be briefing about the project in the next class or not. Yeah, I will confirm that. We have not decided yet, but the project we are planning to complete the project before the break.
The break is in Thanksgiving break, isn't that correct?
I think so. I am not sure about that.
I think that's what I heard. So if it's Thanksgiving, probably like we have like 3 classes
I think one class is enough to
finish the project.
to brief you.
But you said the project will be due before the break.
Yeah, not before the break. I mean, you will do the project in the break like this.
In the break.
Yeah. So maybe you can submit the project after the break.
So we're doing the project on our own. It's not.
Yeah, I will.
supervised.
Yes, but I will try to brief as much as possible, because it will take some time that it cannot be covered inside the class maybe. But the things are very small, simple, that can be done in home actually. But yeah, we will decide on that actually. Let's see how much time it takes to brief. So yes, I think this is it. This is it for, we can call it a day maybe.
Yeah. So just to wrap up, this project, you said it can be a group project.
Yeah, this will be a group.
Is every group doing the same thing? They're using the photosensor,
Exactly.
using the Arduino, using the coding. It's a similar thing. Right? It's like an exercise to learn this one. It's not designed yet.
When we will deal with, it's a kind of design as well, because it's just this array is nothing but some random signals, but we have to process it. So there will be some processing involved. I think we will do the processing inside the code. So that will be a pretty design task. That should be a design task.
How are you deciding on the groups? Like,
I have to talk with Dr. Aditz, and then I will just inform you in the Google Classroom. Yeah, because we have to purchase these things, and we also have to talk to Dr. Fatih as well about the photodiodes and how many groups we can have. Yeah, we have to discuss it.
Yeah.
I think, yeah. So that's it for today. Thank you so much.
Yes.